Okay, if not, let us start talking about negative feedback. Oops. Now, I seem to have. Oh, no. Okay. So, what I really want to do is not cover the entire screen, because sometimes I might get disconnected and not know that I got disconnected. Okay, so today's topic is that of negative feedback. And while this is a very, very important topic in today's electronics, it started out rather badly for this particular concept, because one of the first things you will realize that negative feedback does, especially when you apply it to an amplifier, is that it makes its gain go down. Okay, that sounds like a bad thing to happen, because if you really are designing an amplifier, anything which reduces the gain seems to be somewhat of a bad thing. So, in the early days of electronics, negative feedback was never even thought of as a design strategy. In fact, nobody wanted to even actively think about it. Any kind of feedback that people talked about was the other kind, something called positive feedback. But then people saw that circuits which should otherwise work fine and give you large gains behaved rather erratically. Sometimes the gain turned out to be much different from what they expected it to be. Maybe much more, maybe much less. But you should realize one thing: having a gain which is much bigger than the gain that you designed something for is actually bad. If you want a gain of 20 and your circuit ends up giving you a gain of 80, that's not necessarily a good thing. If you want a gain of 20 and your circuit gives you 25, you can live with it. 80 may be way too much beyond what you really want and may really screw up whatever you want to do with the circuit. Okay. So an erratic gain, something where the gain is much bigger or much smaller than what you designed it for, is not a great thing for a circuit to have. Okay. And people also found some other problems. People found that the circuit suddenly started to oscillate on its own. Now, oscillations essentially mean that a circuit is producing an output even without an input. Now, that may sound impossible, because you might say, where is the energy coming from? That looks like a sheer violation of the conservation of energy. But that really doesn't happen, simply because a circuit, as you must have seen in the amplifier circuits that we have designed so far or talked about so far, all circuits have a power supply, right? At least a DC power supply. So the source of power is always there. But even if you don't give an AC signal to the input, sometimes the circuit might start producing an AC output of its own. Now, when the circuit does this by design, you call that an oscillator. And that's, of course, a very important piece of equipment, something which can produce oscillations and signals. So all the function generators, etc., that we work with, all signal sources, they are basically some kind of oscillator or the other. But when an amplifier, which is supposed to amplify a given input, oscillates on its own, then suddenly you're getting an output which has nothing to do with the input. And that is something you definitely don't want. And say you were listening to the radio at some frequency and you want your signal to be amplified so that you can hear a loud version of the very weak signal that's coming in. And suddenly you hear a tone which has nothing to do with your signal, maybe some constant tone at some other frequency. That would be a disaster. So circuit starting to oscillate on its own is really a bad idea. You don't really want that. So it so turned out that the culprit in almost all those cases were what is called positive feedback. You wanted negative feedback, or people didn't realize it then, but people slowly realized that negative feedback actually solves this problem to a great extent, and has a lot of other benefits besides. So what exactly is this negative feedback concept? Let's try to discuss that. And we are going to do this, and we start discussing this at a sort of abstract level. Abstract level in the sense that instead of talking about this very specific, say, amplifier circuit, we will just say, let's say we have an amplifier. And what I'm drawing for you now, this triangle, sideways triangle, that's a standard symbol for an amplifier. So those of you who have seen the last video would definitely know that. An amplifier essentially, well, this arrow essentially points towards, from the input towards the output. And here, the reason why I'm using this abstract symbol is right now I'm not interested in what exactly is the circuitry inside the amplifier. In fact, we are not even interested into whether it takes in a voltage and produces a voltage signal and produces a voltage output, or whether it takes in a current signal and produces a larger magnified current, or whether it takes a voltage signal produces a current output. All kinds of amplifiers can be there. Right now, all we are saying is it takes in a signal. Let's just say that signal is X, some X, and produces an output Y. So this X could be an input voltage and Y could be an output voltage for a specific kind of amplifier, but it could be something else. Okay. And let's just say that there is a gain which this circuit has, and that gain I'm going to call A0. The zero for the time being. Why am I using A0 here? This is the gain without feedback. That is, if you had nothing else connected to the circuit, the output Y would have been, okay, this is in the absence of anything else, Y would have been A0 times X. Okay. But now comes the feedback part of the network, and what the idea essentially is, you take a part out of the output, somehow multiply it by a factor beta. So you sample the output, whatever that output is there. Maybe I need to draw it a bit better. Whatever the output is, you sample that. You have some circuitry here which produces a fraction of that, let's say part beta of that, and produces beta Y as its output, and feeds that back to the input in such a way that is actually going against whatever input you are giving. This is the negative in the negative feedback. You feed a fraction of the output back in such a way that instead of aiding the signal, input signal, is actually opposing the input signal. Okay? So is this clear? This is the schematic situation for negative feedback. Here the input could be an input voltage, the output could be an output voltage. You could equally well have current to current amplifiers where the input X is an input current and output Y is an output current. And this signal, this beta, is essentially something which takes a fraction of the output, takes the output current and returns a fraction of it back. Could be a fraction. In fact, this could be a current to voltage amplifier. Now, an amplifier whose voltage output depends on how much current is being fed in. And then this beta would actually not even be dimensionless. This beta would take in the voltage from the output, sample that, whatever that voltage is, and return a current which is proportional to that. So beta here would be a ratio between a current and a voltage. So beta would end up being an admittance in that case. But we will, for the sake of definiteness, we will talk about voltage to voltage amplifiers because they are very common, and more importantly because speaking about one kind, it helps to keep us focused on what we really want. Okay. So now, if you do this, what is the actual input to the amplifier? Can anybody unmute and tell me that? In this scenario, when you have connected the feedback, so now, okay, now you have this original amplifier, and you have on top of that, let's say, at this circuit, within this blue rectangle here. Okay, maybe blue may not be a great color for this. Let's see. Okay, it doesn't really matter. Maybe I will just use a different color for the time being. So whatever is inside the red rectangle is the feedback amplifier. There is the amplifier plus the feedback network. Both taken together gives you what is called the feedback amplifier. So this is the original amplifier which you had. And this one is the amplifier with feedback, or often just called feedback amplifier, which is the circuit that we are actually using. That is this original amplifier plus the feedback network. Now, what is the input to this? The input to this feedback amplifier is, of course, X. But what is the input to the actual amplifier that you had inside? Could somebody just tell me that? That would also prove to me that somebody is listening and not everybody has not gone to sleep.
Sir, X plus or minus beta y.
Well, actually, the whole idea behind negative feedback is that it's X minus beta y. Okay. The fraction of the output is supposed to feed back in out of phase to the input. So it's supposed to go against this. Okay, so this is the actual input to the amplifier. Of course, this tells you that if you multiply this by A0, what you're going to get is the output, right? A0 is just a fraction which connects the input to the original amplifier to its output, and the output is Y. So this is what you're going to get, right? And an immediate consequence of this will be a very trivial rearrangement would tell you that Y by X, this ratio, which, remember X is the input not to the original amplifier but to your feedback amplifier. X is what you're giving in here. The amplifier is actually getting X minus beta Y. That is why the amplifier is producing X minus beta Y times A0. But what is the overall circuit's gain? The gain of the overall circuit is, of course, its output, which is Y, divided by its input, which is X. And what is that going to come out to be if you just rewrote this a bit? You would immediately get this, right? Just move the beta A0Y from here to the other side and then divide by it. And this is it. That's your gain. Okay? So, can anybody tell me what would I ever achieve by this? Because this looks like I've deliberately reduced the gain a lot, right? The gain was A0. Now I brought it down by a fraction, 1 plus beta A0. And if A0 is huge, then even for a reasonably small beta, a small fraction, beta A0 may be quite large. In fact, beta A0 may be much bigger than 1. Which would mean that the gain has come down a lot. So this is the first thing that happens. If you have a negative feedback, this reduces the gain. Okay, so why should anybody want to do it? What possible advantage can this give? Reducing the gain? Any ideas? If you want an amplifier, why sort of shoot it in the foot? Now I can come up with some more examples of that from real life of negative feedback, but I don't really want to go into that right now. But one thing that you see is negative feedback sort of makes something underperform, apparently. And that's sort of understandable, right? Something is trying to produce a big output. You want to bring it back. You're reducing the input by that. Yeah. Any ideas?
In order to limit the amplification, but I don't understand that, because couldn't we just change the internal circuitry instead of doing this entire?
Yeah, that's a very good point, except that there's a problem with changing the internal circuitry. You could of course bring down the gain by changing the circuit. But the real problem with doing that is the gain in a circuit, for example, this A0, the raw gain of the circuit, would depend on active components, like the transistor, for example, in the examples that we have dealt with so far. Okay. Now, the real problem is a transistor, while it's great at amplifying small currents into large currents and hence transferring small currents from one resistor to a larger current to another resistor. But that's exactly what the transistor means, by the way. Transistors is an acronym for transfer resistor. It transfers current from one resistor to another. As a result, it produces a large output voltage from a small input voltage. But the problem with the transistor is how much the gain will depend strongly on the transistor's parameters like the beta or at least HFE, HIE and all these values. And these are actually rather fickle. They tend to change with various conditions. They might say the beta might change because of temperature, might change because the operating voltage has changed, because the bias has shifted for some reason. Or even worse, suppose your transistor blows out and you replace it by another transistor from the same batch. Unless you have paid through your nose for a very, very high quality transistor, what will happen is that the beta of two transistors of the same batch may be very different. So one may be 200, the other may be 250, maybe 300. And the real problem would be that controlling the gain by changing the circuit directly without using negative feedback, just relying on the fact that the transistor that you're using. Okay, unfortunately, there are two betas right now, so I will not talk about the transistor beta, I will say transistors HFE, which is roughly what its beta is, right? I have a feedback factor fraction beta as well. So just to keep things straight, let's talk of the transistor as having an HFE. Now this HFE changes drastically from transistor to transistor within the same batch, changes drastically with temperature, changes drastically with operating point. Again, not necessarily very drastically, but quite a lot. As a result, what happens is if you did not have feedback, the trouble would be setting the gain at a right value or keeping it close to whatever value you want may be very, very difficult. That gain tends to drift quite a lot. So just take a look at another way of writing this expression for the gain with feedback. Now this way of writing the thing should give you a big hint as to why you want negative feedback here. This is the actual gain of the full feedback circuit, and if A0 is very large, which often can be easily achieved, say at least if A0 is such that 1 by A0, of course if A0 is very large, then 1 by A0 is very small, and if 1 by A0 is say much less than beta, then beta may be 1/10, but 1 by A0 may be 1/200 or 1/300. If this is achieved, then what happens to A? A becomes at least approximately, if you can neglect the 1 by A0 with respect to beta, A becomes 1 by beta. Now, why is that a great thing to have? Can anybody suggest that? It should be pretty easy to judge that from what I've said so far. Why would one love to have A given by 1 by beta?
This won't depend on the transistor characteristics.
This will not depend on the transistor. In fact, this will not depend on the active components that you are using. Transistor, of course, is just one example of an active component you could use. There could be other things that you could use inside your amplifier. But most active components, things which really cause amplification, most of them tend to be rather fickle. They tend to change quite a lot with various conditions. Whereas this beta is essentially the fraction of the output voltage. Let's keep talking about voltage to voltage amplifiers for the time being. Beta samples the output voltage, returns a fraction of that back to the input. And if that happens, well, you could also do it by something as simple as a resistor network, a pair of resistors. Say, just a series potential division. If you do that, The important thing to realize is resistors are very much more stable under variations of condition than active components are. So it's unless you completely mess up your design, beta would be something which hardly changes with changes variation of operating situation. In fact, even say, even if you were worried about temperature varying a lot, first of all, you may be able to put your negative feedback circuit, part of the circuit, far away from transistors and other things which tend to heat up a lot during the operation. So the temperature of your negative feedback network may not change very much. But even more importantly, if you have made resistors out of the same material, if you are using two resistors out of the same material to have a potential division, the resistances are going to change with temperature in the same manner. So the ratio, which is what decides what fraction will go out, that will be temperature independent. Okay. So the point is 1 by beta is definitely a lot less than A0. That's what it's supposed to be. Okay. Remember, for this approximation to work, beta must be much bigger than 1 by A0. That means the final gain that you're landing up with 1 by beta may be quite a lot less than the actual gain or the raw gain that your amplifier really had. However, the new gain that you have is something which is much easier to control. It's something which you can say with a guarantee that it's going to stay pretty close to what you want. So let me just give you an example here of with numerical values. Let's say A0 is say 200. Okay. And beta say is 1 by 10. So the actual A is going to be, of course, 200 by 1 plus 20, right? So 200 by 21, a bit less than 10. Okay, right? But now, just imagine that due to some fluctuation, A0 changed and went all the way to 300. And that's quite possible. Maybe you change your transistor, and the transistor HFE for another transistor of the same batch changed drastically, and you end up with the A0 raw gain of 300. So how much does A change? It changes to 300 by 1 plus 30. 300 by 31. Of course, 200 by 21 and 300 by 31 are not both the same, but they are both pretty close to 10. And okay, you can just carry out the calculation and figure out that the percentage change in A is going to be a lot less than the 50% change in A0, right? So you end up with a circuit with a lot smaller gain, a gain of only 10, because gain which is of the order of 1 by beta, right? This is just 10 is just 1 by beta. And that's the approximate value that we say. The important thing is, once A0 is large enough, 1 by A0 is small compared to beta, so it doesn't matter whether A0 is 200 or 300, you end up with the same or roughly the same gain. So this stability is essentially what you're looking for in many circuits, and negative feedback allows you to have this kind of stability. Relying on active components and designing your circuit differently may not be a great idea, simply because your active feedback components may very well float with time for various reasons. In fact, okay, I will talk about that later perhaps. I'm not sure that whether anybody has, or most of you have watched the last video, which was about things like input impedance and output impedance. But let me just quickly remind you of what these things are, because we're going to need that to describe what else is good about negative feedback. One thing that we see is great about negative feedback is just this, is the fact that negative feedback reduces the gain but makes the gain a lot stabler. Okay. The other things which are impacted nicely or positive, okay, impacted positively on by negative feedback sounds like an oxymoron, but that's what we are really going to talk about. So let's look at the effect of negative feedback on input impedance. Input impedance was a topic that we talked of the last video, input and output impedance and stuff like that. But I'm not sure everybody has watched that. So let me just quickly tell you what the input impedance really is. If you have an amplifier, then if you look at the amplifier from the point of view of the outside world, of course you have a source which is connected to it, and the source will have its own impedance RS. Every source has some impedance. A great source has very little impedance, but a not so good a source, and sometimes we cannot even choose the source because maybe you are using a particular microphone which has some large impedance. You can't do without it. So let's say the source has some input impedance, some impedance of its own, but what does the amplifier look like to the source? As far as the source is concerned, the source doesn't really care with what the amplifier does with the signal it gets. All the source sees is that there is something connected to it which is going to drain some current out of it. That's it. As far as the source is concerned, whether that current is then used to heat up say some oven or somewhere, or whether it is amplified to produce a larger signal or not, doesn't really matter. Okay, so as far as the source is concerned, all it sees is something which is drawing some current, and that is what is called the input impedance of the amplifier. So effectively, as far as the source is concerned, it's just an impedance. The amplifier is just an impedance. Of course, as far as the load is concerned, something which you connect to this side, as if you look at it from the side point of view of RL, it looks like something quite different. This is something we have described in detail in the last video that I put up. But right now, let's look at just this much. Now, if you have a voltage to voltage amplifier, the important thing is you have a signal voltage that is being fed to the circuit, but the amplifier, of course, does not amplify the signal voltage, right? What does it amplify? Which voltage does the amplifier amplify? Again, a question which somebody should answer.
The signal voltage minus
If
the
you have an
voltage drop
amplifier,
across RS.
True,
Low.
correct. But what I meant was a wording which is shorter. It's just the input voltage, right? Okay, that's exactly what it is, what you said. The reason why the input voltage differs from the source voltage is that because the amplifier is drawing some current, there will be a drop across the source impedance, right? Because there is a drop, because there is a current being drawn. Okay, so basically, the input voltage to the amplifier, what is really being amplified by the amplifier? Of course, the amplifier doesn't really know how much the source voltage is. All it can handle is, all it can modify is what it gets. It gets VI. And VI is simply ZI by ZI plus RS into VS. And that gets amplified. Okay. And this, an amplified version of this is delivered ultimately to the load resistance. So the details of this, or exactly how to calculate the ZI for a particular circuit, we have discussed in some detail in the last video. But the question I have for you is this. What would you want ZI to be, large or small? Yes? Remember, your aim is to have a voltage to voltage amplifier, something which takes in a voltage from the source, produces an amplified version at the output. So would you want the ZI for such a circuit to be large or small?
Small.
Now, if you had a small input impedance, what would happen is a large amount of current will be delivered by Vs, right? But if the current delivered by Vs is large, the drop across RS is going to be large, which means the actual voltage which the amplifier gets is small. Or you could just look at this formula. What is it telling you? It's telling you that a fraction of the signal voltage is going to the amplifier. What fraction? Simply the potential division formula is what is being used here, Zi by Zi plus Rs, right? And if Zi is small, then this fraction is going to be small, right? The larger Zi is, the bigger this fraction is. In fact, if Zi is very, very big, much, much bigger than Rs, then you can ignore Rs with respect to Zi and you will get 1 here. That means the entire signal voltage goes to the amplifier and gets amplified. So if you wanted a large gain, you would of course want Zi to be large, right? You would want this condition, not small. Small is exactly what you don't want. A small input impedance for a voltage to voltage amplifier. Now these needs to be sort of put in with their own caveats. When I say input impedance should be very large, I mean for a voltage to voltage amplifier. If it's an amplifier which amplifies current, where the output is proportional to the current it gets, then of course its Zi had better be small, because you would want as much current as possible to go into the amplifier then. Is that clear? If Zi were infinitely large, that would mean it would draw no current while connected to Vs. That would mean the entire Vs would drop across Zi. That sounds a bit counterintuitive to begin with, but you should get used to that. Large resistance may end up meaning large voltage. If you are talking of, it will end up meaning large voltage. You are talking of series potential division. Now, why do I want Zi to be much, much bigger than RS? It might simply appear that we want Zi to be much, much bigger than RS because we want the gain to be large. Because this, of course, is just the first step. Vi goes to the amplifier, then it gets amplified. But if what goes to the amplifier is already reduced a lot because of drop across RS, then you're going to get a low amplification. So making Zi huge, of course, makes the amplification large. But that is, once again, is really not what you want, or not your, okay, it's not correct to say it's not what you want, but it's correct to say is that's not your primary concern. Your primary concern is this: the source is outside the amplifier, right? If something is outside the amplifier, then the person who made the amplifier has no real control over it. Somebody might use a different source with the same amplifier, right? You may want to change your microphone or some other device from which you're getting your input. You don't really want to keep it tied to one thing and one thing only. So RS might very well fluctuate, right? So you may have a 10 ohm impedance mic. You could, tomorrow you bought a new mic, which is maybe great in other aspects, but has 100 ohm impedance. So RS might change from 10 ohm to 100 ohms. Now, if your Zi was only 100 ohms, then what would happen is for RS equals 10 ohms, let's say Zi is only around 100 ohms. Then if RS is 10 ohms, Vi becomes 100 by 110, that is 10/11th of Vs. So, a smaller value than Vs, but not very much smaller. But if then your RS changes because you change your mic to 100 ohms, for this, Vi will change to, well, change to a very small value, right? It will become half of it. So then 100, that will become half of Vs. So your circuit, which was producing a reasonably large output, now suddenly produces a very small output, simply because you change your mic. The way around that is either force the user never to change their mics. Say that, okay, you never use a mic with input impedance or with internal impedance more than say 10 ohms. Or, and this is what is much better, design your circuit with a Zi which is much, much bigger than whatever RS you can think of using here. So if your RS is at say 100 kilo ohms, then whether you are putting, sorry, not 100 RS, sorry. If Zi is 100 kilo ohms, then whether RS is 10 ohms or 100 ohms will make hardly any difference. Once again, it's the stability of the behavior of the circuit which is important. You want a large Zi simply because you want the circuit to be stable. Clear? That is the real point. You want large Zi, not so much because it's going to give you a bigger gain, but more because it will give you a gain which protects you from fluctuations because you're changing your source resistance. Now, let's think of what happens to this Zi quantity if you have negative feedback. So this is the original amplifier with some Zi. Okay, so let's call that Zi O. or Zi0 for the original amplifier. Actually, by the way, I've been calling this zero here, or whatever looks like O or zero up here, A0, and I just call this Zi0, but it really stands for O, capital O, because this really is called, this O stands for open loop. Now, I'm pretty sure most of you are aware of this. When you say open in electronics, what you mean is some circuit is disconnected. It's off. The loop in this nomenclature is actually the feedback loop. Open loop means the feedback loop has been opened out. It has been disconnected from your circuit. So ZIO is simply whatever you have, whatever input impedance you have without the feedback. Okay? So maybe what I will do is I will just blow this up a bit. Oops. So you have a input impedance ZIO. This is, sorry, bad positioning. For your circuit, you also, of course, have a gain AO. So let's not call it A0, let's call it AO, open loop gain. And the A, by the way, the result that you get for the circuit with feedback is also called ACL. CL, of course, here standing for closed loop. So let me point out that this is again what's going to happen. You have an input. Well, X here, since we are talking about voltage to voltage amplifiers explicitly, let's no longer keep it that abstract. Let's call this VI. Call the output VO. So this was what we were calling X before. And this is what we were calling Y before. Because we are now specializing to voltage amplifiers, we are saying this is the input voltage, that's the output voltage, and a fraction of the output voltage, a fraction beta of the output voltage, is taken and fed back to the input in such a way. So this is really, okay, schematically you put a sigma sign there which shows that you're summing up these two quantities. And I will talk about how to do this in a circuit. This is just a schematic. But basically you get the idea. You take the output, sample a part of it, feed it back against the input. So now what is going to be the input impedance to this particular circuit? Okay, the answer here is simple. How much is the current that is going to flow in? Now, okay, before we go any further, let's also confess that this schematic that we have used, and we have already used that even in the last calculation that we did, but we did not really clarify that at that point. The schematic is sort of an idealized version where we assume that it takes, this beta is taken from the output without loading the output. That is, it doesn't draw more current from the output and is being fed back here without drawing current. Okay, that's actually not really possible in most realistic circuits. In most realistic circuits, the moment you connect the feedback loop, the currents also change a bit. That is, the current which is being driven here, a part of the current will also flow either in or out of the feedback part. So the input current to the amplifier and the input current to the original amplifier would really be different. Similarly, the output current which is coming out of the amplifier here and the output current which will come out of the full amplifier, which is the amplifier with the feedback network, they may very well be slightly different. But for the sake of simplicity, we are assuming that we have a feedback network which does not load either the input or the output. If there is a loading, you have to take that into account, so that will modify your calculation somewhat. But the basic idea or the basic result will stay the same. So we are looking at this more from a schematic point of view and trying to see what will happen rather than, or roughly what will happen rather than exactly what will happen. But anyway, for the timing, just if you ignore that some current is drawn at this by this input, this fractional circuit, and some current is either fed in or taken out at this node here, if you just ignore this part, then it's very easy to see how much the output is going to be. Notice that what is the voltage here? It's not VI, it's VI minus beta VO. Right? Is that okay? This is just what we did earlier, just X and Y has been replaced by VI and VO. So that's the actual input voltage. And this, of course, AO times that, this was our VO, this is what we used a while ago. But right now we are focused more on how much current is flowing in, because that will help us determine what is the input impedance of the circuit with feedback. The current which flows in is simple. It's just this voltage VI minus beta VO, which is what the amplifier is actually getting, divided by ZIO. Right? This is the current which is flowing into the amplifier. How much current is being delivered by my source here? If this current is I, how much is this current? Yes? Yeah, any ideas? If this current which is being fed into the original amplifier is I, how much current is the input actually putting into the full amplifier, the amplifier with feedback? If nobody had responded 5 minutes ago, I would have understood, because I did not give the clarification 5 minutes ago. But I have already given you a huge clarification about how this feedback network is supposed to work, and that should immediately tell you how much this current is going to be. If this is I. Yes? I'm waiting.
VI by ZI.
No, first of all, that's the final. If this is I, how much is this? A simple question. The current which is going into the actual original amplifier is I. How much current is going into the overall amplifier? The overall amplifier, remember, is this whole thing. So let me just draw the rectangle once again for you to remind you that this is this rectangle, red rectangle here is the full amplifier. And this was the original circuit to which you have added the negative feedback section. So how much current is the actual full amplifier getting? Okay, I saw an answer in the chat box, but it looked like there was an emoji there. So I'm not sure whether did you say I with a what? I1? Can you tell me what this emoji is? This an emoji? I don't even know. Or was it an attempt at a smile?
It was a mistake. Sorry.
I into 1 plus B. Not really. It's much simpler than that.
It's I.
It's I. Of course it's I. Come on. That's exactly what I've been. That's why I said that clarification that I gave a while ago. Without that, it could have been a difficult thing to figure out, because you would worry about, okay, I goes here, how much goes here? But I just said that I'm assuming an idealized situation where the negative feedback network does not load either the input or the output, doesn't draw any current, doesn't drive anything else. So Kirchhoff's law would tell you, oops, I need to, that this current is going to be simply I, same as this current, right? Because there is no other way the place the current could go to. This, whatever current goes here goes into the amplifier. That's what we are assuming. In a real life negative feedback network, this may not be possible. So that will modify your final result somewhat. But in most cases, negative feedback networks can be designed in such a way that they draw very little current from the input. So we are assuming that that has been done. So now comes the question, what if that is I, then what does the source see? Source sees that, okay, I am giving a voltage Vi and I am giving the current that is being drawn is I. So what is Z? What is the input impedance for the actual circuit? That's of course Vi divided by this current, right? That's what the impedance looks like, right? I have a voltage of Vi across the amplifier input, and the amplifier is drawing a current I from me. So Vi divided by I is what impedance the amplifier looks like. But now this is very different from ZIO. By the way, it's even easier to figure out what this is going to be. To remember, Vi minus beta Vo, what is that? That's just Vo by A. AO, right? Remember, this thing times AO was VO. So that's all we have put in here. If we just divide this VI by I, what you're going to get, this I, what you're going to get is simply ZIO into AO, this denominator, divided by, well, VO goes down, VI is up here, so VO by VI, which is what is VO by VI? VO by VI is the actual gain, and the actual gain is 1 plus A beta. Wait, what happened? I seem to have messed up somewhere. Wait a minute, Vi by the current, that's right. And the current would mean ZIO, AO, that's also right. VO by VI. Okay, so VO by VI, that's the actual gain, that's fine. Perfectly all right. So this is VO by Vi. So what is this value? This is ZIO AO. Does anybody remember what VO by Vi was? It was not AO, right? AO was the gain without feedback. This is the gain with feedback. Smaller value, AO by 1 plus A beta. So finally, what happens? What I get out of all this is the input impedance of the circuit with feedback, Zi, is actually ZIO, that without feedback, times 1 plus A beta. So what has happened? The input impedance of the circuit has gone up by this 1 plus A beta factor. Okay. So in our example where we had beta equals 1/10 and A equals 200, this is the input impedance of your actual amplifier, the full amplifier, is 21 times bigger than the input impedance of the original amplifier. Remember, having a large input impedance is good for our amplifier, simply because if you have a large input impedance, your circuit, the behavior of your circuit is stable from fluctuations in the RS. And negative feedback ensures that happens, ensures that the input impedance goes up. Okay. Well, we also talked about output impedance in the last video. I'm pretty sure most of you haven't seen it yet, but do see it because it's important. And the output impedance, well, having a large output, what is the output impedance? It's basically what happens when you look at the amplifier from the output's point of view. There, the output essentially sees the amplifier as if it's some amplified version of the input, right? But just like any voltage source, it will have an impedance which comes along with it. This is the so-called output impedance. Of course, here, can anybody tell me, would you want ZO to be large or small if it's a voltage to voltage amplifier? Notice what is going to happen. The output should be AOVI, but the actual output, which falls across the RL is not AOVI. It's a fraction. Why is it a fraction? Because there's a division of potential between this ZO and RL. So what would you want? Would you want ZO to be large or small?
Zero should be small.
Why? Why should it be small?
So that the potential difference across RC is large.
Okay, that was RL, not RC. That's my bad
RL.
handwriting. Okay, L for load. Anyway, could be O or whatever. RL, that's the output voltage, output resistance. So what's good? What's the good thing about it being large?
So that's what we want, right? Because it's an amplification circuit.
Okay, that would be one way of looking at it, because I do want an amplified version. But that's once again not the real thing that you want. What you want is a stable output more than a large output. You could change your RL. The RL is outside your amplifier, right? Depends on, maybe it's a speaker. So it depends on which speaker you're using. Change your speaker, RL will change. If ZO is small compared to whatever RL you have, if ZO is much smaller than whatever RL you can have, it doesn't matter how big RL is. Then whatever RL is, the entire AOVI is going to fall across RL. So it's not being large which is important, it's being independent of what RL is. So you could equally well use a small speaker or a large speaker and you would expect your circuit to still work. Of course, a large speaker usually takes a lot more current to work, so that may not always be great because your circuit may not be able to deliver that much current. But as long as your circuit works, different speakers with different impedances could just as well work for the same circuit. Simply because if ZO is very tiny, it doesn't really matter how big RL is. The fraction that you get in the output is RL by RL plus ZO. Okay. But remember, here the fraction is ZI by ZI plus RS is what, because this is what you want to come to the amplifier. And here RL by RL plus ZO, because you want to figure out how much from the amplifier is going to the load. And this quantity, if ZO is very tiny, is very nearly 1. Doesn't matter how big or small RL is. Okay. So you want a very small output impedance. And I will not calculate this to you for the simple reason that I've run out of time, and also because I need something to go into the assignment. If you put in negative feedback, you just saw that what negative feedback does to the input impedance is that it raises the input impedance. What does negative feedback do to output impedance? Actually, it lowers the output impedance. This is something you're going to show in an assignment, that this is what actually happens. Okay, this is small O, that's capital O for the open loop. And this is what happens to output impedance. The output impedance actually goes down. So negative feedback actually makes the circuit behave a lot better as a voltage to voltage amplifier than it would otherwise. It does cut down the gain, but makes the gain more stable and makes the input impedance go up, makes the output impedance go down. Those are things which you would want. In fact, there are other things which I will not talk about now because it will not make much sense unless you see the video that's coming up, which is about frequency response. But you should remember from whatever we studied about filters, that for circuits which have capacitors, etc., like you may have a behavior like this, where for the amplifier, this is what you have. This is the subject of our next video anyway. You plotted the gain of the amplifier versus frequency, you will find a region. I've talked about that briefly in the video which has already been uploaded, but the details are in the next video. There's a region of frequencies which is called the mid-band frequency range, where the gain is independent of the frequency. If you go below that, the gain falls down. If you go above that, the gain falls down. So just as for filters, you look at those frequencies for which the gain falls down from the flat peak value by a factor of √2. √2 again, there's a voltage gain falling down by √2 means power gain falls down by a factor of 2, and that's the 3 dB frequency, 3 decibel. I hope people still remember that much from the theory of filters that we talked about a long time ago, near the beginning of the course. But anyway, you have a lower cutoff frequency and an upper cutoff frequency. These, and the gap between them is the bandwidth. So this is what tells you how large a frequency range is it over which you can use your amplifier. What negative feedback does, and again this is to be something which we will talk about later, as well as we will do the details in an assignment. What negative feedback does is that it lowers the lower cutoff and raises the upper cutoff, which means the circuit works for even lower frequencies and up to even higher frequencies, increases what is called the bandwidth of the amplifier. So all kinds of good things come out of negative feedback. And just one final thing, there's a, if you read different books, the sign of beta might change from book to book. But the important thing is in all versions, A beta, this thing has to be positive. So suppose your amplifier has a negative gain, which simply means your output is out of phase with the input. That is, when the input goes up, the output goes down. That's also amplification. In fact, our C amplifier is like that. It produces a negative gain. Then your beta would also have to be negative in such a way that you end up with this kind. So 1 plus A beta is what you would always have as more than 1. That's how you get negative feedback. If 1 plus A beta were less than 1, you would end up with positive feedback, which has its own advantages in some cases and own problems, because it makes the circuit more unstable, more prone to vicious fluctuations and so on. So we'll discuss all that in the next another class. But the reason why I stress so much on negative feedback is one of the biggest things that you do in an op-amp circuit is an op-amp has an immense gain. The gains that we have been talking about for the transistor amplifier, op-amp's gain is nowhere compared to that. It's way, way more. Say 10,000, 20,000 range easily. But the great thing about it is you never use that raw gain. What you do is put negative feedback on it if you want an amplifier. And that makes the op-amp circuits very, very easy to both decode and figure out what they do. Also, it makes the op-amp circuits very good as far as stability and other desirable considerations, desirable things are concerned. Okay, so that's all for today.
Excuse me, sir.
Any questions? Yeah.
So just a small logistical query. Is the assignment due tomorrow or on Sunday?
Is it what?
The assignment, I mean,
It's on Sunday. Did I by any mistake write Saturday?
Yes, sir. It was written 7th, so we thought it was.
Okay, so I must have messed up my calendar. Okay, my calendar shows both Saturday and Sunday as S. So I must have got confused. It will be Saturday. And there was a question about the beta value to be used for the transistor. For a second question, that has to be, just take whatever HFE is given for the other part of the question, use that as the beta. And for cut-in voltage, unless otherwise stated, use 0.7 volts. That was, you needed to calculate the bias for one part of the question. For that, you would need beta and V gamma. By the way, you will find that the circuit does not depend very strongly on beta. So if instead of 200, which the value is, which is the HFE given, but use some other value, say 100, you would still end up getting somewhere roughly in the same neighborhood. Well, that's actually part of the design, right? If you have a negative emitter bias feedback, its job, by the way, emitter bias feedback is negative feedback, and that's why it stabilizes. It stabilizes against variations in beta and so on. So we did not use the negative feedback language so much there. I did explain why it works as part of the video, but maybe I did not use this language so much. But you can easily see that as a negative feedback which tries to bring down the input, because when you have a resistor on the emitter side, any change in the current would make the voltage drop across it larger. That would make the emitter go higher, and that would make the base emitter voltage, which is the actual voltage which controls all the currents, come down. So the input goes down with the rising output. That's what negative feedback is. And that is why the emitter feedback resistor actually stabilizes. Okay, any further questions? I will just change that, and I have to put up the link. I don't think I put up the link. Have I? I don't remember. I need to put up the upload link as well, and it will be Sunday. Don't worry about that. Okay, if there are no further questions, stop the recording.